Good day. I'm going to discuss another topic entitled Quantitative Approaches to Industrial Management. So, introduction, management science or operations research. Management science or operations research is the quantity or quantitative approach to management decision making. So we can call this one as MS as an abbreviation for management science, or OR for operations research. As it is commonly called, this helps managers make better decision or decision making. Successful managers used quantitative approaches to their decision-making process. So when is it needed? When the problem is complex. Second, the problem involves many variables. Third, there are data which describe the decision environment. There are data which describe the value or utility of the different possible alternatives. Number 5, the goal of the decision maker or her organization can be described in quantitative terms. Number 6, workable models are available for these situations. An MS or OR specialist would likely follow the 6 steps in the MS or OR process in making managers make better decisions. So we have 3 columns here. So their descriptive title, process activities, process steps, and the process output. Under the process activities, under site visit, conference, observation, research, these are actually the process being conducted when formulating the research. So the process steps, step 1, you need to observe the problem environment. Then what is your process output? Sufficient information and support to proceed. Another way of performing the process activity is to define use or define your objective or define also the limitations of your study. Then the process steps, under step 2, analyze and define the problem. Then your process output, you must have a clear grasp of need for the nature of solution requested. Under the process activity, so either it is an operational research, so the tool or MS, the interrelationships, you need to utilize here mathematical models, known solutions to approach the research. Under the 3rd step of the process step, you need to adopt a type of model. So you need to develop here a model. So the process output model that works under stated environmental constraints. And then next is either it is an internal or external data, facts, opinions, computer data banks are needed to suffice the process of activity. Then your process step, under step number 4, select the appropriate data input. So you need to have a process output. If you have sufficient inputs, so therefore you're able to perform here the necessary model to operate. Under the process activity, testing the limitations or even verifying it. Under the process steps, step 5, provide the solution and test its reasonableness. So the process output, solutions that support current organizational objectives. And then finally, under the process activities, there is a behavioral issues, selling the idea to the management involved, or probably even getting the management involved in undertaking this research phase. So under the process step 6, implement the solution. So the process output, ownership by the management, sufficient to support longer run operation of the model. MS or operational research today, activities have grown rapidly in business. Government units and private institutions simultaneously, the scope of the problems addressed, the MS or operational research practitioner has expanded as well. So in the 1950s, this came the birth of the Operations Research Society of America, or abbreviated as ORSA, and the Institute of Management Science, also known as TIMSS, in 1948. The English organized the Operational Research Club. So more recently, MS or Operations Research Society have been formed in many countries, some with their own journal or bulletin. Quantitative methods to be discussed is the queuing theory only. Although, despite there are other models other than the queuing theory, like probability concepts, forecasting, decision theory, and Venturi models, linear programming, simulation, and number 8 is network scheduling. The topic will only cover the queuing theory. So, queuing theory studies the random arrival at the servicing or processing facility of limited capacity. Models also allow management to calculate the lengths of future waiting lines, the average time spent in line by a person awaiting service, needed facilities addition, and the service levels or capacity that minimizes the sum of waiting cost and operating cost. Waiting lines, queuing models, introduction. An important class of management science problem involves situations in which waiting lines occur. Examples bound in our daily lives. We commonly encounter waiting lines at gas stations, stop signs, supermarkets, restaurants, newsstands, and other places, such as airports. We often experience waiting line in transportation systems such as planes circling an airport awaiting clearance from the control tower, trucks waiting to load or unload cargo, buses back up waiting to enter a terminal, cabs queuing up at airports, and train stations waiting for passengers, or passengers queuing up waiting for cabs or taxi. The ferries queuing up, waiting to offload passengers and autos. Frequently, there are waiting lines at banks and post offices, factories, jobs queue up, awaiting processing. Most of these systems are characterized by highly variable arrival and service rates. The concept of the queuing model and queuing analysis can be particularly useful to decision makers who must make capacity decisions. Queuing models suppose that the mean arrival rate of a car at a car wash is 4 cars per hour, and this arrival rate can be described by a Poisson's distribution formula. Therefore, the mean time between arrivals is 15 minutes. So, example, the reciprocal of the arrival rate of 4 vehicles per hour, which is actually fractioned or equivalent to 1/4 an hour. So the solution here is 1 hour is equivalent to 60 minutes. So let us use some useful arithmetic way of devising or solving the problem. So in 1 hour, there is 60 minutes. And then there are 4 cars that enter in an hour. So therefore, there are 15 minutes interval. So the ratio is another solution. So 1/4 is equivalent to 0.25. So 0.25 hours times 60 minutes. So you will be able to arrive same answer as 15 minutes. So let us now tackle the basic single channel model under queuing theory. So this model pertains to situations in which there is one channel or one server that processes all customers waiting for their service. So note that if a group of servers works as a single team that processes all customers, not that if a group of server works as a single team or channel, that situation would be considered as a single channel system. So a single channel model is appropriate when these conditions exist. Number one server or channel. Number 2, a Poisson arrival rate. Number 3, a negative exponential service time. Number 4, processing order is first come, first served basis. Number 5, the calling population is infinite. Number 6, there is no limit on queue length. So these are the formulas for basic single server model. So the performance measurement using the system utilization, where P is the system utilization, percentage of time server as occupied. So these are the formulas that we need to use in our model. So I would like you to look at it carefully, how these formulas are actually used or applied in this particular problem. So for number 2, the average number in line, LQ is the average number of waiting for service. So this is the formula for it. And letter C, the average number in system. L is the average number in the system waiting for or being served. And letter D, the average time in line, WQ, is its average time customer must wait. So it has something to do with the average waiting time for service. And then letter E, average time in system, where capital letter W is the average time customers spend in the system waiting for service and service time. While for letter F, probability of 0 units in the system, PO, meaning there's no need to wait or there's no waiting time at all. So therefore N is 0. So for letter G, the average waiting time for an arrival not served immediately. So where WA is the average waiting time not served immediately. Now let us discuss here example 1. Performance measurement from number waiting time to waiting time. The mean arrival rate of customer at a ticket counter with one server is 3 per minute, and the mean service rate is 4 customers per minute, and the mean service rate is 4 customers per minute. Calculate each of the performance measures listed in the table above, where alpha means arrival rate. So the alpha symbol is 3 per minute, and mu symbol means the service rate. So the mu equals to 4 customers per minute. So if you're going to apply the formula given a while ago, so under system utilization, we just denote here the mean arrival rate, alpha is 3, and for the mu arrival rate, its mean is 4 customers per minute, which is equivalent to 0.75 or 75%. While for letter B, the average number in line waiting for service is LQ. So the average number in line waiting for service is, we have 3 minutes raised to the second power, then divide it by 4 times 4 minus 3. So here we have LQ is 2.25 customers. So this is the mean average for the average number in line. So therefore, there are more than 2 customers in an average. So average number in the system. So here, using the formula as what we have discussed a while ago. So for L, we have we just substitute here those values that were already computed. So here, the LQ is 2.25 plus the system utilization, which is actually equivalent to 3/4. So therefore, average number in line waiting for the system, L is equivalent to 3 customers. So there are 3 customers in line waiting for their service. So there are 3 customers on an average. So the average time in line, this is already, we are already discussing here the waiting time, where WQ is equivalent to LQ divided by alpha. So the average time spent waiting, waited by the customer per minute, is 2.25 customers divided by 3 minutes, which is equivalent to 0.75 customers per minute. Then under letter E, the average time in the system is the formula here, and substitute the given datas. So we have 0.75 plus 1/4 is equivalent to 1 minute. So this is the average time spent in the system waiting to be served. So what is the probability of 0 units in the system? So meaning, what is the average system where customers won't wait? So therefore, probability of not waiting, which is equivalent to 0, is equivalent to 1 minus alpha divided by mu. So therefore, substituting here the given values, we have 0.25% where customer won't wait. So if you're going to analyze it, 25% customers won't wait in the system, while the probability that an arrival will have to wait for service, so P, or this is already represented by letter P, equals to alpha divided by mu. So 3 divided by 4 is 0.75. Therefore, there is greater chance that customer will wait for their service. So this is the probability that there is a higher chance that customers will wait for their service as compared to 25%. Under letter G, average waiting time for an arrival not served immediately. So WA equals to 1 divided by mu minus alpha. So 1, therefore, divided by 4 minus 3. So WA is equivalent to 1. So therefore, the average waiting time for an arrival not served immediately is 1 minute. Under transportation queuing, since the time humans first gathered into societies, there have been queues. They have existed whenever people have demanded more of a service than that service could provide. Though queuing is by no means new. The study of queues is relatively recent, dating only to the beginning of the 20th century and the work of A.K. Erlang. So the research of queuing in transportation have evolved in its own distinct direction. in part due to the influence of Newell's work, and in part due to the unique aspect of transportation system. Unlike applications of queuing in communication or production, queues in transportation tend to be much more predictable, and as a consequence, much of research in queues in transportation has been directed at non-stationary time varying system. Non-stationaries arise in transportation because people prefer to travel at set times of the day and week, largely corresponding to their work schedules. These demand surges create much of the QE in transportation. And in many transportation systems, mass transit, trucking, railroads, and intersections, customers are served in bulk. From the standpoint of capacity provision, transportation often relies on major investments in infrastructure such as roadways, runways, or railroad lines. Infrastructure intensive systems have only limited latitude for adjusting capacity to respond to fluctuating demand. Thus, queues recur at known times when customers arrive at a faster rate than the infrastructure can accommodate. So another unique aspect of transportation is that the customer service mechanism is often defined by the spacing between vehicles along a guideway, and not by how quickly a person or piece of mechanism or equipment can process customers. Thus, the time to serve a customer is determined by the customer's behavior. So a queuing system also behaves as a continuum of uh, serial servers with extremely short service times interacting with each other. Therefore, the system model depends not only on the number of customers that queue at a particular location, but the physical length of that queue and whether that queue spills back into other servers. This phenomenon are the core subject matter of traffic flow theory. History of research on transportation queuing. Nearly all of the public research on queuing in transportation is motivated by a modal application, such as vehicles on roadways or mass transit. Nevertheless, there is considerable crossover in concepts and methods between modes. This section provides a few examples. Traffic vehicular flow on highways, traffic signalized intersections, transit and tracking, aircraft and airports, railways, bus terminals, and shipping docks. Example number 2 is the performance measures. The owner of a car wash franchise intend to construct another car wash in a suburban location. Based on experience, the owner estimates that the arrival rate for the proposed facility will be 20 cars per hour, and the service rate will be 25 cars per hour. Let's assume, for the sake of illustration, that both arrival and service rate are Poisson's formula. Note that a Poisson's distribution service rate is equivalent to an exponential service time. So the service rate will be variable because all cars are washed by hand rather than by machines. Cars will be processed one at a time, hence there is a single channel or one server system. So we need to determine the following. So letter A, the average number of cars being washed. Letter B, the average number of cars in the system either being washed or waiting to be washed, for a case where the average number waiting in line is 3.2. Letter C, the average time in line, the average time cars wait to get washed. Letter D, the average time cars spent in the system waiting in line and being washed. So the system utilization system average number in the waiting line. So this is actually the table for it. So take note, for the table average number in the waiting line, this is the formula, where LQ is the average number customers in the waiting line for service. Then here, the average number being served, where the rate is equivalent to alpha divided by mu. This is the average number of being served in the service or in the system expressed in rate. So the next row here is the average time, where in the waiting line, which is actually represented by WQ, which corresponds to the average time customers must wait in line for service. So when we say W, this is best expressed as wait, while L, which actually represents as the waiting line or line for service. So therefore, the average time being served in the system is 1 divided by mu, where alpha means the arrival rate. So there are 20 cars per hour, while for the mu, which actually serves as the mean service rate. So when you say service, this is the work that have operated during that time. So mu, therefore, there are 25 cars per hour wherein the car wash boys could attend while catering their clients. While here, when you say alpha, these are the mean average, where cars would actually wait for their service. So there is actually a mean arrival rate of 20 cars per hour. So therefore, the solution, average number being served, is the rate, or R, is equivalent to alpha divided by mu. So here we have a rate of 0.80 or 80%. So LQ is the average number of customers car in waiting line for service, which is 3.2. So how did we arrive to this? Of course, you were able to assess this 3.2 through averaging. So this can actually be performed through actual count or through observation. So meaning this is already the value for it, where LQ is the average number of customers' car in the waiting line for service. All you need to do is just look at your watch. Then presuming that for these 20 cars, so you get the average mean, which if you're going to total it, then divide the value by 20, we were able to come up with the value of 3.2. So solve for the following. L and WS, where L is equivalent to LQ plus alpha divided by mu. So now in the system, so what I have done here is to expound further the formula under this table. Then we were able to come up and devise this system in the waiting line and being served as compared to this table a while ago. So now I have reintegrated here a more precise table, so we would understand further how we were able to solve the following required problem. So L is, this is the formula for it, where you can actually translate L equals to LQ plus alpha divided by mu, which if you're going to simplify the formula, you can even adapt this as L equals to LQ plus simply the rate. Because if you're going to look at this formula, alpha divided by mu is actually a rate, which you could actually see it in this formula, which is actually the answer here is 0.80. Now let us look at the other formula. So for WS, so this is the average time in waiting line and being served. So therefore you just utilize here WQ, which is in the waiting line. So this is actually WQ, and then being served plus 1 divided by U. So therefore WS is, you just add up these two formulas, then you are able to come up with the formula already. While for L, if you're going to look at the table, this is LQ plus the rate formula. So now hope that you were able to understand the formula here. So the average number in the system is LQ plus rate, or alpha divided by mu, which is L equals to 3.2 plus 0.80. So therefore the average number in the system waiting for their line is 4 cars. So letter C is the average time in line. So the average time cars wait to get washed. So LQ, which is actually 3.2 number of cars. So where did we get 3.2? As noted a while ago, this is where we took 3.2. Then add the rate, which is actually 0.80. So therefore there are 4 cars. So now let us go back here. So WQ is the average time in line, or the average time cars wait to get washed. So WQ equals to 3.2 number of cars divided by 20 cars per hour. So therefore WQ is 0.16 hours. So to compute it, we need to convert hours to minute. So 0.16 hours times 60 minutes divided by 1 hour. WQ therefore is 9.6 minutes. So this is the average time in line waiting to get washed. the average time cars spent in the system. So this is the waiting in line and being washed. So WS equals to WQ plus 1 divided by mu. So a while ago, we made use of 0.16 hour plus 1 divided by 25 cars per hour. So therefore, WS is 0.20 hour. So we need to convert hour to minutes once again. 0.20 hour times 60 minutes divided by 1 hour. So therefore, WS is 12 minutes. So it means that the average time cars spent in the system waiting in line and being washed is 12 minutes. Now, let us once again proceed to the system utilization, where P is equivalent to alpha divided by S times mu, where S is the number of channels or servers, and P is the system utilization, percentage of time servers are occupied. Note, in order for a system to be feasible, underloaded system utilization must be less than 1. So P therefore is alpha divided by the number of servers or channels in the system times mu. So take note that P is equivalent to 20 cars per hour. So we only have a single channel. That is why it is equivalent to 1 times 25 cars per hour. Or we were able to arrive at 0.80, which is actually equivalent to 80%. So the system utilization, we have 80% service time. So meaning we have a high efficiency rating in terms of service. So this is the ratio how to determine the capability of the car wash business. It is actually 80%, which is an excellent work. So this ends our presentation.